Hello, statistics students. Previously, we learned what was called a one-sample hypothesis test, where we compared mu or p to some constant, mu0 or p0. In the next several lessons, we're going to do what's called a two-sample hypothesis test, where we're going to compare the mu of this group to the mu of this group, or the proportion p of this group to the proportion p of that group. So this is a two-sample hypothesis test, and you'll find that it's pretty similar to what we've done previously. So let's take a look at where we should start. We need a couple of definitions. First off, are our samples independent or dependent? If they're independent, life is pretty easy. If they're dependent, we're going to do matched pairs, which you might recall from early chapters on experimental design. So here we have two populations. The first population has a mean of mu1 and a standard dev of sigma 1. The second population has a mean of mu2 and a standard dev of sigma 2. Now, if we want to do a hypothesis test and see if these two means are equal, we would write it this way, our hypothesis. If I want to know, is this mean 5 units greater than this mean, then we would write it this way. Now, on page 420, he said 420, on page 420 of your textbook, it says that you could write this as mu1 minus mu2 equals 0. I encourage you not to do that, because mu1 minus mu2 equals 0, we're going to reserve that for matched pairs. And if we see mu1 minus mu2 equals a different constant, like in this case 5, we can't say mu1 equals, I guess we could say mu2 plus 5, but that's not very helpful. We want it written like this. So if they're equal, I encourage you to write your hypothesis like this. If they're not equal, or if we're doing matched pairs, you can write it this way. As I said, the hypotheses are listed on page 420 of our current textbook. And they encourage you to write them this way. Again, mu1 equals mu2, there's your equal sign here, and here's your equal sign here. So you could write this as your set of hypotheses, or this, or this. Now over here it says you can do it this way, but again, I encourage you not to. In fact, in a bit, I'm going to encourage you not to use mu1 and 2 as subscripts. So in our first section, we're going to assume that we know sigma 1 and sigma 2. In other words, we know the population standard devs of the two populations we're studying. Let's take a look at the conditions under which we could do this hypothesis test. First, we have to know the two standard devs. What do you think is going to be in the next section where we don't know the standard devs? Okay, so we have to know the standard devs. The samples have to be randomly selected. They have to be independent. And either the populations are normally distributed or the sample size is at least 30. When those conditions are met, we'll have a sampling distribution for if you take x1 bar minus x2 bar for each sample and do those differences, you would get a sampling distribution of the difference of the sample means, and it's going to be approximately normal with a mean of mu1 minus mu2 and a standard error of this. We'll talk about where this comes from. Now, back when we were doing one sample, all those hours, days ago, This was our z statistic. And our denominator was sigma over root n, because that was the standard dev of the sampling distribution, what we call the standard error. You'll notice that you could also write it this way, because if you take the square root of sigma squared, you get sigma. The square root of n, you get square root of n. But you could write it this way. So now if we're comparing two standard devs together, instead of x bar, we have x1 bar minus x2 bar. We want to know the difference. How far apart are those two sample means? And then here's the hypothesized difference, mu1 minus mu2. Well, if we're saying mu1 equals mu2, then this number would be 0. And then what we're going to do for the denominator is, rather than sigma over root n, we're going to take sigma squared over n for the first population. We're going to take sigma squared over n for the second population. We're going to add those together and then take the square root. Notice that our sample sizes from our two populations don't have to be the same size. You could pick a sample of 10 from population 1 and a sample of 40 from population 2. Now all this mu1 and mu2, and now I'm going to tell you don't use mu1 and mu2. You should use subscripts that are descriptive. And the reason for that is, if you're saying mu1 and mu2, I don't know which group in your problem we're talking about is 1 and which one is population number 2. You got to make it clear for me. So in this example that I give you here, if we want to know whether the average adult man is 5 inches taller than the average adult woman, we'll use mu sub m for the average height of the men and mu sub w for the average height of the women. That way you could do mu sub m minus mu sub w equals 5. And then the alternative would be no, it's not. So on page 422 of our current textbook, there is a problem. And it says, a survey indicates that the mean annual wages for forensic science technicians in local and state governments are $55,950 and $51,100 respectively. The survey includes a randomly selected sample of size 100 from each government branch. 100 from local, 100 from state. Assume that the population standard devs are $6,200 for local and $5,575 for state. The two samples are independent at a 10% alpha. Is there enough evidence to conclude that there is a difference in the mean annual wages? So our null hypothesis is mu local equals mu state. And again, note my subscripts. I didn't use 1 and 2. I used local and state. We weren't told which one was expected to be higher, so either they're the same or they're not. Either local governments pay on average the same amount that state governments do, or they don't. Alpha is 10%. So my z statistic, the difference of the two means, well, if I'm saying they're equal, no, I'm sorry, my mistake, that's the samples. So we just subtract the two samples. Here, if we're saying mu L and mu S are equal, then that difference is going to be 0. So it's this difference minus 0 divided by, and then we have a local standard dev squared over a sample size and a state standard dev squared over a sample size. And we end up with a z statistic of 5.82. So I need to go 5.82, because this is a two-tail test, I need to go 5.82 standard devs away from the mean this way, and 5.82 standard devs away from the mean this way. You should be able to tell from your experience with the normal curve right now that both of these numbers are approximately 0. But you could look them up if you want. Then you're going to look them up in the table and find that that number's too small and that number's too big. So if you go way off the table to the left, it's just going to be approximately 0. So there are two ways we could reject the null. We could use our little quote here where we compare p to alpha, or we can compare our test statistic z to critical values. We're going to do both. So on the left side in blue, I want the probability that z is less than negative 5.82 or greater than positive 5.82. Both of these areas are the same area, so I could go 2 times one of them, and either one of those is approximately 0. So 0 is less than 10%, p is less than alpha. So I'm going to reject the null at the 10% level, and there is sufficient evidence to say that the average salaries of the two groups are not equal. Now, I can't say that the local pays more than the state, because my hypothesis was either they're equal or they're not. I didn't know which one paid more. Now, if I wanted to prove that on average local governments pay more, I would have to collect new data and do that hypothesis test. So are we in the rejection region? This is our p-value method. So if I have a 10% alpha, that means these two areas together have to add up to 10%, which means 90% in the middle. And we can know that our z critical value is 1.645 plus or minus. Well, our z statistic was 5.82, so we are very much in this rejection region. So we reject the null at the 10% level and conclude that there is sufficient evidence to support the alternative, which is that the two average salaries are different. So there isn't a lot new in this lesson. Sure, we've gone from one sample to two, and we've changed the formula for a z-score slightly, but they make sense. They follow from one another. So life should be a lot easier this chapter than last, because last chapter you were learning it from scratch. This chapter you have a basis to fall back on. So that's all I have. Have a great day.